Today we will study the resistors in series and in parallel, and then we will look at more complicated circuit, and then we will calculate the power in electric circuit. So let's start first with the resistors in series. When we have resistors that are connected in series, then the equivalent resistor would be the summation of those resistors. Now, what is the definition of the series? If I have a resistor that I'm calling R1, and then I have another resistor here that is R2. Now, if I connect those two resistors right here with no other components sharing this node, then I can call R1 and R2 connected in series. So in this case, if I want to find the equivalent resistance for those two resistors that are connected in series, then the equivalent resistance, R equivalent, would be as simple as adding those two resistors. So R1 plus R2. This basically will ensure that my current going in R1 will be the same going in R2. So in other words, by not having any other components sharing this node, this means that I have the same current I here going through both of them. In this case, I will call those two resistors in series. And this is the expression to calculate the equivalent resistance for those two resistors that are in series. Now, let's assume I have more than two resistors. I have R3, I have R4, and of course at the end they are connected to the battery that we talked about. So here, this battery is generating the potential difference such that this is positive, this is negative. In this case, because the current here, so we agreed upon this convention that this current, the positive direction, is leaving the positive terminal, and then it will come back and enter the negative terminal. So this is my current. So as you can see here, my current I, which is the same current going into R1, R2, R3, and R4. That's why I call those four resistors connected in series. And the equivalent resistance for those two, for those four resistors would be R equivalent equals to R1 plus R2 plus R3 plus R4. The summation of all those resistances, because they are connected in series. Now, there's something important here also, that the potential difference across R1 here, remember in resistors, the current always enters its positive terminal and leave its negative terminal for the resistors. So in this case, I have here delta V1, which is potential difference across R1 only. So in this case, I can say delta V1 equals to what? Equals to R1 times this current. Fine. Now what about this delta V? Well, since this delta V is across all of them, then it makes sense that my delta V will be R equivalent times I. So at the end, the potential difference would be across the resistance that I'm interested in times this current. So here in this case, delta V1 is I R1, delta V2 is I times R2, and so on. Now let's look at this example. Here in this example, we have two flashlight bulbs, each with 12 ohm resistance. They're connected to a 6-volt battery as shown. So it is very important to know that those two light bulbs, they are connected in series. Why in series? Because they share this node and there are no other components sharing that node. In other words, if I have another light bulb, for example, connected here, this means this light bulb will not be in series anymore with this light bulb. Why? Because there is another component that is sharing this node. Now, what's that sharing going to do to my current? Well, this sharing is going to break now my current into two currents. And in this case, this current that I talked about is not the same going into the second light bulb. So having this light bulb sharing this node basically makes that current, make those two light bulbs not in series. But right now, since there is no other component sharing this node, this means the whole current I is the same going into the first light bulb, and it is the same going through the second light bulb. I need to calculate the current, and as you can see, the current is going through both of them, and I have my potential difference is the one that across both of them. So I cannot ignore this one and only do the current for this light bulb. No, since this potential difference delta V is across the equivalent resistance of those two light bulbs. In this case, I will have to find the equivalent resistance of those two light bulbs. Those are in series, and now in series resistors are added, and 24 ohms is the equivalent resistance for those two light bulbs. And in this case, if I want to calculate the current, I know this potential difference that now across this 24 ohms, then in this case I equals delta V over R. I have here the potential difference 6 volts. I have the resistance that this potential difference is across 24 ohms. Then the current is delta V divided by R, and this is going to give me 0.25 ampere. Now, those resistors may be connected in a different way, as we will see here. So we saw that when those two resistors were in series, they share the same current. Now, if I have resistors in parallel, and the main point about the parallel, let's talk about the parallel. I have two resistors that are in parallel if they share both terminals. So this is R1, or they share both nodes, as we will see later on, and this is R2. If they share both terminals or both nodes here, regardless of whatever is sharing those nodes, as long as both of them are sharing both nodes, in other words, as you can see, R1 is connected to R2 from both sides. There is nothing in between, nothing here in between. No, they are connected directly with a wire like this from both sides. In this case, I can call R1 and R2 connected in parallel. And what is the expression that allow me to calculate the equivalent resistance for two resistors in parallel? It is 1 over R equivalent, so the inverse is the summation of the inverses plus 1 over R2. If I have more resistors, R3, then basically I can add it as 1 over R3. Now let's assume I have this circuit now, as you can see here. For that circuit, if this is R3, this is R4, this is R5, and this is R6, we can say that R4 is not connected in parallel with R3. Why? Because it's not sharing both terminals or both nodes here. As you can see, it is only sharing one node here. This other one is going through R5. So R4 and R3 are not in parallel. Are they in series? Are they in series? The answer is no, they are not in series, because they have other components, as you can see, sharing this node between. So they're not the only two resistors that are connected through this node. There are other components that are also connected to that node, so they're sharing this node. And there's a current going in here. In this case, they don't share the same current, and this basically means that they are not in series. What about R4 and R5? R4 and R5, yes, they are in series. They share this node, and as you can see, they have the same current going through them. What about R6 and R0? R6 and R0, they're not connected, neither in series nor in parallel. There is no clear definition to that, except they are part of the circuit. But they are not in series, they are not in parallel. If I don't have this branch, and my circuit is as this, in this case, yes, I can say that R0 and R6 are connected in series. Why? Because now the same current here, I, that's going to go through this equivalent resistor, is going to continue going into this R6. Now, resistors in parallel, they don't share the same current. However, they share the same potential difference. If you look at the potential difference across R3, it is delta V3. If you look at the potential difference across R2, it is the same. It is delta V3. If you look at the potential difference across R1, it is also the same. It is delta V3. Why? Because those wires are ideal wires, as we agreed upon, and they have zero resistance, which means the potential here is the same as the potential here, is the same as the potential here, which means that those 3 points, they have the same potential. Those 3 points, they have the same potential. Then the potential difference across R3 would be the same as the potential difference across R2, the same as the potential difference across R1. So now we know what is the difference between the series resistors and parallel resistors. Let's move on and do some examples. In this example, as you can see, we have 3 resistors. Just by looking at those 3 resistors, I can say right away that those 3 resistors are in parallel. Why? Because they are sharing this node such that R3 is connected from both sides, as you can see, with R2 and R1. No other components in between, so only with wires. In this case, I can call R1 and R2 and R3 as resistors connected in parallel. Now, what is the potential difference across each resistor? So this is interesting. We need now to do some calculations. Let's first draw the circuit. I have here R1, I have R2, I have R3 connected to potential difference, delta V equals to 15 volts. I need to calculate the potential difference across each resistor. Isn't it the same Isn't it delta V equals 15 volts is the same potential difference across all of them? It is. Why? Because there are only wires between those all up to here, which means those ideal wires will make sure that this potential right here at the negative terminal will show up here, will show up here, and will show up here. The same thing for here. The same potential would be here, would be here, would be here. It will be the same anywhere on that wire. So in this case, the potential difference across R1, across R2, and across R3 equals to 15 volts. So I have delta V1 equals to delta V2 equals to delta V3 equals to delta V equals to 15 volts. So this is A. Now B, what is the current through R3? If I want to calculate the current through R3, in this case, what shall I do? I know the potential difference, delta V across R3. Then I can apply Ohm's law. As you remember, Ohm's law says delta V equals to R times I. So if I need the current, we need to find the current through R3. In this case, using Ohm's law, we can say that I3 equals to delta V divided by R3, and in this case, I3 equals to 15 divided R3 is 150, and then I3 equals 0.1 ampere. Now, if I want to find I1, which is the current through R1, then I1 is 15 divided by R1, 250, and I1 equals to 0.06 ampere. So it's a very important observation here that the relationship between the current is inverse proportional. We have the resistor at 150, then the current through it was 0.1. We have the resistor going up, and the current went down. So this is V. What is the equivalent resistance of the circuit? Well, 1 over R equivalent equals to 1 over R1 plus 1 over R2 plus 1 over R3, then 1 over R equivalent equals to 1 over 250 plus 1 over 150 plus 1 over 150. Work out this equation, then you will find that R equivalent equals to 58 ohms. E, what is the current through the battery? The current through the battery is based on Ohm's law, delta V equals to Ri. In this case, I will have to use the equivalent resistor in order to find the total current, which is the current supplied by the battery and also coming back to the battery. In this case, I equals to delta V divided by R equivalent, and I, the current, equals to 15 divided by 58. Then I equals to 0.26 ampere. So this is the current supplied by the battery, and also that's the current that is entering the R equivalent. In this example, we have current travels through a light bulb. We brought a wire that has a zero resistance, that's an ideal wire, and we connected it across the light bulb as shown. Essentially, all of the current continues to travel through the light bulb. Is this true? Or half of the current travels through the light bulb and the other half goes into this wire. or all of the current travels through the wire, or not enough information provided. Definitely all the current is going to flow through the wire. Why? Because this wire has a zero resistance, and in this case, he has shortened out the light bulb. So that's what happens when you have a short circuit, for example. Basically, you have shortened out this component, and now all the current will go with a maximum capacity through this wire, bypassing this light bulb, and that's why the light bulb will stay off. Okay, so for this circuit shown, the current through the 20 ohm resistor is 0.16 ohm. So he gave me the current going into this resistor. And now he's asking me what is the potential difference across the battery. We don't know the potential difference across the battery, so how can we find this potential difference across the battery? First of all, I'll redraw the circuit. I need the circuit. I have here 25 ohm. I have 15 ohm. And this is my 21 ohm. And here the current going through this is 0.16 ampere. And then my battery that I don't know the potential difference. This is what I want to calculate. So in this case, let's see what we can do. We have the current going into this branch. Now, this current is going to split into those two branches. However, if I found the equivalent resistor for those two, then in this case, I can find the potential difference across here. We'll see how we're going to do this. So we have a 21, then I have R equivalent. I have the 21. I have the battery. So let's calculate R equivalent. 15 and 25 are connected in parallel. So R equivalent equals to 1 over 15 plus 1 over 25. If you work it out, it will be R equivalent equals to 9.38 ohms. Then in this case, if I want to calculate the potential difference, total potential difference, which is across this R equivalent that is in series with the 21 ohm, then I can say R total equals to 21 plus this R equivalent, or R total equals 21 plus 9.38, which means R total is 30.38 ohms, and in this case, the potential difference V equals to R tot times I, or delta V equals to 30.38 times 0.16. Delta V equals to 4.86 volts. Okay, moving on. In this circuit, we need to identify the circuits that has R1 and R2 connected in series. And remember, we said that R1 and R2, they're connected in series when they share the same node, and no other components are sharing that node, which basically means that they don't have the same current going through them. So in this case, R1, no. What about, circuit 1 is wrong, is eliminated. What about circuit 2? Well, circuit 2 has the current going through this, R equivalent. So if you think about it, if I am to simplify this, now here, if this is R1, and this is R equivalent, and this is R2, coming back to here. In this case, as you can see, although they don't share that, but it is basically the same path, and all of them are having the same current, which basically the sharing, the same node that we talked about, as if they are adjacent, just to give you a simple idea, sharing the same current. And here in this case, in this circuit, yes, R1 and R3 and R2 are connected in series because at the end they have the same current going through them. So this circuit 2 is right, and this circuit 3, as you can see here, they have the direct sharing to the node. Here they are indirectly sharing the same current. So I have circuit 2 and circuit 3, and this makes the answer E is the one. Okay, in the following circuit diagram, which ones have resistors R2 and R3 in parallel? Again, let's evaluate circuit 1. You have R2 and R3 in parallel. I can see that they are sharing both nodes here. Then this one is yes. R2 and R3. What about this one? I think yes, they are, because as you can see, don't let the drawing here mislead you. At the end, you need to look at the electrical connection between R2 and R3. At the end, yes, they are sharing both and they have the same potential difference, which means that R2 and R3 are in parallel for circuit number 2. So I have circuit 1, circuit 2, and circuit 3, no, they are in series. Then this makes it only 1 and 2. So the answer is D. Now let's move on to the power. We said that the power is the time rate of the energy either supplied or absorbed. In the case of the battery, we have the power being supplied. And for the case of the resistors, we have the power being absorbed by those resistors. Remember, the unit for the power is watts or joules per second. At the end, the power equals to the potential difference times the current, either for the battery or for the resistors. The only difference that the battery is supplying power and the resistor is absorbing power. So let's look at this example here in this circuit. What is the power provided by the battery? In order for me to calculate the power provided by the battery, I need to calculate the equivalent resistor. For example, I can calculate the equivalent resistor, and then from calculating the equivalent resistor, I can use Ohm's law, calculate the total current, and then I can find the power provided by the battery. So let's do this. Let me redraw the circuit again here. So we have R1, we have R2, we have R3, R1, 150 ohm, R2, 350 ohm, R3 and 550 ohm. So in this case, we need to calculate the total resistor, the equivalent resistor for R2 and R3 that are connected in parallel. So I have R equivalent equals to 1 over R2 plus 1 over R3. So in this case, 1 over R equivalent equals to 1 over 350 plus 1 over 550. Work out the equation. Our equivalent would be 213.9 ohms. Then our total is R1 plus R equivalent. Those are in series. Then our total is 150 plus 213, 363.9 ohms. This is the R total. Then I can now find the total current going through this R. From Ohm's law, I have I equals to delta V divided by R total, or I equals to delta V, which is 35, divided by 363.9, and then I equals to 0.096 ampere. So this is the current, the main current going in here, 0.096 ampere. I need to find the total power. The total power is P equals to delta V times I, and in this case, and the power P would be delta V, which is 35, times 0.0996, which means that the total power supplied by the battery is 3.36 watts. B, what is the power consumed by each resistor? So in this case, I know P1 equals to delta V1 times I1. And delta V1 here in this case is R1 times I1. So I have R1 times I1 times I1, or P1 is R1 times I1 squared. And I1 is the same as the total I here. I1 is the same as the total I, 0.096 is the same as I1. And in this case, I have P1 equals to, the R1 is 150 times I1 0.096, and this is a square. And in this case, P1 would be 1.4 watts. So this is P1. I need now to find P2. Now notice here that I did calculate R equivalent. So if I multiply the R equivalent with I, 0.096, I get the delta, the potential difference between R2 and R3 in this case. So here, if I say delta V2, which also equals to delta V3, and this equals to R equivalent times I, in this case, delta V2 that equals delta V3 equals to R equivalent, which is 213.9 times 0.096, and in this case, delta V2 equals delta V3 equals to 20.53 volts. Now I found the potential difference across our equivalent, which is the same across R2 and the same across R3. Then I can say P2 equals now to delta V2 times I2, right? Then I don't know I2, then I can say P2 equals to delta V2. I don't know I2, but what I know delta V2, I2 equals to delta V2 divided by R2. So in this case, I know P2 is delta V2 squared divided by R2, and in this case, P2 will be 20.53 squared divided by 350 ohms, and P2 is 1.2 watts. I can calculate P3 with the same way. I know P3, again, delta V3 squared divided by R3. I can use this right away. And P3 is 0.77 watts. Now, if you add the power consumed, should be equal to the power absorbed. So let's add P2 plus P3 plus P1 equals 2. We have 1.4 plus 1.2 plus 0.77. The total consumed equals to 3.37. Here, the one that we calculated is 3.36, which is almost due to tolerance. That's the same. Okay. So last slide. We have in this circuit a circuit that has a switch S. This switch, when it opens, it breaks the current into the circuit. There will be no current going into the circuit. When it's closed, you can replace it with a wire. So in the circuit shown, the battery provides a constant potential difference between its terminals. With the switch S open, the current at position 1, I1, is 4 ampere. What are the currents at position 1 and 2 in the circuit when the switch is closed? Okay, so let's first draw the circuit to understand what's going on. So here, we will draw two circuits. Because we have a switch, we will draw two circuits, because this switch is giving me a circuit when it was open and another circuit when it was closed. So let me start first when the switch was open. When the switch was open, my circuit's going to look like this. Here, S is open. My circuit is going to look like this. What happened to the branch that has the switch open? Well, since there is no current going into this branch because the switch was open, then the whole branch is eliminated. So here we have the current I1 and I2. I2 is 0 when the switch is open, because the branch is open, no current going into this circuit, then definitely right away I know I2 is 0. I know this one 10 ohm. The whole branch with the switch open now would be completely removed. It will be useless. It will not contribute to anything. Okay, so the question is asking, find the current when the switch is open, and then when the switch was open, the current was 4 ampere. Now let me draw the circuit when the switch is closed. Again, when the switch is closed, you can replace it with a piece of wire. 10 ohm, 10 ohm, current here, I1, and the current here is I2. So when the switch was open, I know I1 was 4 ampere. What are the currents at position 1 and 2 in the circuit when the switch is closed? Now remember, this circuit is completely different than that circuit. And I suggest that you put a prime right here, because those variables are now completely different. So the current will change in the circuit when I do any physical change. So let's see what we can what information we can extract when the when the switch was open that does not change when I close the switch. One of those parameters that do not change is the potential difference across the battery. The potential difference across the battery has nothing to do with the switches. It will always give you the potential difference that it's supposed to give you. Either if it's open or closed, it doesn't matter. But what I can get from this 4 ampere is to calculate the potential difference here. Why? Because I know that delta V equals to I times R. And I know the current going through this resistor. I know the resistor, then delta V is 4 times 10, delta V equals to 40 volts. Okay, this is useful now. This is very important and very useful. Now I can take this delta V that I found from knowing the current when the switch was open and come here and use it here. So when the switch was open, he gave me an information that made me find or calculate this delta V that I'm using it in the second circuit. Now I need to calculate the current at position 1 and position 2. Remember, we said this is prime, so it is not 4. I here is not 4 anymore. Why? Because now I physically changed something in the circuit. So now the readings will be different. What are those readings? The currents. The currents will be now different. Now I need to calculate I1 and I2. So how do I do this? Well, I know the potential difference delta V is the same across both resistors. So I can calculate I2 prime. So I know delta V from Ohm's law, I2 prime equals delta V divided by the resistor R. So I2 prime is delta V, which is 40 divided by 10. I2 prime is 4 ampere. I2 prime is 4 ampere. What about I1 prime? I1 prime, I need to calculate now the total resistor The total resistance here is those two resistors in parallel. A rule of thumb, if you have two resistors that are connected in parallel, if they are equal, the equivalent is half right away. Where did I get this one from? Well, 1 over R equivalent equals to 1 over 10 plus 1 over 10, right? Then 1 over R equivalent is 2 over 10. Then R equivalent is 10 over 2. R equivalent is 5 ohms. So in this case now, I know the equivalent resistance for this circuit. I know the potential difference. I can find I1 prime equals to what? Equals to delta V divided by R equivalent. I1 prime as delta V as 40 volts divided by R equivalent, which is 5, and then I1 prime equals to 8 ampere. So I1 prime is 8 ampere, I2 prime is 4 ampere. So now let's go to here and see I1, 8, I2 is 4, and the answer is 8.